probability, discrete random variables, and then I will move on to the notion of independence of discrete random variables. Okay, and of course, if there is time, I will work out a few problems. I should just say at the outset that I might be disrupted a couple of times. Um, yeah, so let us start. I think I wrote down some questions, so let me do those problems. Yeah. So these are questions taken out of the book. I will do these things rather quickly. Maybe there are several subdivisions, but I may just do some of them and not all of them. Remaining are left for you to do by yourselves. Okay. So first question: find the mass function. Find C so that f of x is the mass function of uh, mass function of a random variable, of a discrete random variable, of course, random variable x that takes values in positive integers. Okay, so where? So f of x is equal to, these are easy problems. So you see c times 2 power minus x. So this is subdivision A, division B. I may not discuss everything. F of x is equal to c by x square, and d c rather, f of x is equal to c 2 power x by x factorial. Okay, and these have some special names also. So this is I think maybe called geometric. This one is called modified Poisson, and this is maybe inverse square. Some names, naturally suggested names. Okay, so the first one uh, is, mind you, in all these things, you are told already that x takes values in positive integers. So x, so I don't need to write that. Let me write x belongs to natural numbers, and in all these problems. Okay. So, of course, C must be greater than 0. If C is 0, F will be identically 0. That's not okay. But the main thing that helps you to compute is that since fx, x going from 1 to infinity, x, mind you, is a natural number. This must be equal to 1. So in all these things, this is the thing that you are going to use, condition. We must have, well, for problem A, so subdivision A, C times summation. So let me write here C1, C2, C3 because it's easier that way. C1 times this, 2 power minus x. So this you know how to add. X is equal to 1 to infinity is equal to C1 times. 1 by 2 divided by, so this sum is what I am adding, sorry. Okay, so 1 by 2 is the first term, and then the common ratio is this. So this is the summation. So that is C times 1, C1 times 1. So we must have this is equal to 1. 1 equals this. So this implies C1 equals 1. And the remaining problems are more or less the same. I mean, it's the same logic, but this one you probably haven't. So you see, when you simplify for B, so you get we get 1 is equal to C2 times summation 1 by n square. Let me write use n instead of x, 1 to infinity. Of course, you know this is convergent, but it turns out that this value is pi square by 6. So if you know that, you can write C2 times pi square by 6 is equal to 1. Therefore, C2 is equal to,
So how do
yeah,
we know zeta 2 equal to pi square by 6?
yeah, that's not easy to prove. So I'll pause. You know, hmm, it requires some effort to prove it. You need to know a bit of analysis to do these things. I don't think there is a very elementary proof. Uh, yeah, it's not easy. By
Yeah,
the
so
way,
in exam, if it comes, like we can just say that it is inverse of that, that will that keep it as that sum?
inverse of what?
If like zeta equal to 1 by zeta 2, will that suffice if it for
Yeah,
example?
yeah, yeah. Yeah,
Okay.
so I was about to say that. So the zeta function is defined like this, summation 1 by n power s. And of course, you can allow s to be complex numbers to begin with. I mean, there's a lot to say, but just even think this is what is called the Riemann zeta function. I think it was introduced by Euler. Anyway, so the main thing is that if s is bigger than 1, this is convergent. That you must have studied. And the zeta
If
values,
real is greater than 1, right?
so I'm just
That
confining myself only to real numbers. So s real numbers first of all. And okay, if you know some complex analysis, you know you can extend it as a meromorphic function to the whole of this except for a pole at s equals 1. But I'm not going to discuss all those things. Just think of this. And then zeta values for 2k are known. K, so an positive integer. So 2k, these are known. And in fact, it is always of the form some pi power, whatever, I think pi power 2k, k equals times some rational number. Okay, some rational number. So some number mm, or in rationals. Uh, this you can prove. Okay, requires some effort, but one can do this. If you study some basic course in number theory, there it may be proved. Okay. Now I cannot resist but say that for odd values, it is not even known whether it is transcendental or real. I mean, transcendental or rational or some. What is its behavior? It's not known. It's a major result that zeta 3 is irrational. Okay, so this is sort of telling us that these numbers are rather mysterious. Okay, but for even values, it is pi power 2k times some rational number, and this you will know when you study some number theory. Anyway, I'm not going to that, but it's just this an occasion to talk about it. Okay, so therefore C2 is equal to 6 by pi square. Okay, fine. So C The third one, you should know it. I think here, well, I mean, it is 2 power x by, uh, okay, x factorial. What is that? So, summation, summation 2 power x by x factorial, x going from 1 to infinity. No? Well, if you add it from 0 to infinity, so e power recall, e power x is equal to summation. So sorry, that's an x here and this thing. Let me write here. I don't like x as a variable, but e power lambda is equal to lambda power x by x factorial. But this begins from 0 onwards, x equals 0 to infinity. Therefore, so recall this, then you can rewrite this as, well, the 0th term is missing, otherwise it is e square, so it should be e square minus 1. Therefore, so you can continue. Therefore, C3 must be equal to 1 by e square minus 1, whatever it is. Okay. All right. So let me proceed. It's not my intention to discuss all the problems, so I skip a few problems and discuss this. So I don't remember the problem number, so I just put a dot here. SK denote the set of all integers, positive integers with exactly k digits, in base 10. Okay, usual number. So okay, yeah. So if okay, a fair coin is tossed, uh, how many times? T times, where t is a random variable. T is a random variable that takes values 1, 2, 3, 4, etc. So we just simply briefly say that t is a random number. Okay, so this is a short for saying t is a discrete random variable which takes values 1, 2, 3, 4, blah, blah, blah. Yeah. So t is a random number. Now, what is it that we want to do? So choose, we choose a random number. Okay. Mm, yeah. So, I think this is given. Hmm. Let me just look at the book. The way I have written it, it looks incomplete. Please, just one second. I just check how it is made. Uh, okay. So there is another number. Let n be uh, mm, well, actually, this is again a random number. Okay, random number. So where? Okay. Uh, so what we want to do is uh, find the so chosen from so random number chosen from ST. Okay. Okay. Uh, assume that so each element of ST has equal chance of being chosen, equal chance or probability of being chosen. Okay, in other words, see, you just pick a number, capital N, from the set of course, positive integers. Okay, it will have to belong to ST for some T. Now, what is the probability? Somehow, I don't like the way the book has worded it, but this is what he means. So, uh, uh, we pick a random element and say from ST, each such element having equal probability, what is the mass function of N? So, you see, in other words, yeah, chosen. What is the mass function of N? What is the mass function? I think maybe if I explain this mass function of N. In other words, what you are told is the following. T times where T is a random. No. This I think I made a where until head turns where T is the first time that head turns up. T is okay. T is the first time. Let's say tail turns up first time because otherwise there is no relation. First time tail turns up. So a fair coin is tossed repeatedly T times, if you like. T times, where T is the first time the tail turns up. So that's a random number, right? Now, N is a random number. So, okay, I suppose it's clear. We don't know a specific value for T because it depends on your experiment. You try this experiment, it may turn out that T is some 100, or it may turn out that T is 3, or it may turn out T equals 2, whatever it is. So, okay, T is therefore, you can think of it as a random variable. Okay, so let N be a random number, that is, it's a random variable. And what is its, so it is chose, so as a number, it belongs to some S, it will have some digit, okay? Of course, random digit, because I'm not specifying number of digits. And so what is the condition? So whatever, suppose it has capital T digits, then N belongs to ST. And then once you know that, you know the probability of that N being chosen, because uh, ST is going to be a finite set. We know how many elements there are. There are as many as number of positive integers which have exactly T digits in their decimal expansion. Okay, so decimal digits must be exactly T. And then, of course, the probability of such an N being chosen from this set is 1 by the cardinality of the set Sn. All this is given to you. Only thing you need to find is what is the mass function of N. So you just apply the definition, mass function of N. So Fn of little n is equal to probability that N equals N. And this is same thing as probability of N equals N Well, this can happen. Okay, let me write like this. Given that n is in ST, and this you have to sum over all possible t. No, no, okay, okay. Yeah, that's true. Okay. But once you are given n, this n belongs to a unique t. Okay. What is that unique t? Let me write that. Is this clear? This t equals, okay, sorry, I should write here probability of t. Okay. ST. So probability of t. Uh, t, well, let me write here ST, t equals k. Let me write here k instead of t. This is k, all possible values of k, t equals k. And then here I put k equals 1 to infinity. K bigger than or equal to 1. Okay. Now, of course, there will be exactly 1k for which n will belong to sk. Moment you are given an n, see, this side n is prescribed for you. The moment you prescribe n will belong to a unique sk. Which k is that? Look at the number of digits. So if n is equal to, for example, if so before I, if k, for example, if n is equal to 23075, then then k has to be equal to how many digits? 1, 2, 3, 4, 5. 5 digits. So this number 23,075 belongs to S5. Okay. So there is a unique thing for which it belongs. So that's equal to, but this is easy to compute. This is 1 by, the first one is 1 by cardinality of Sk times probability that t equals k. So where, what is k here? This k, here it is running over 1 to infinity, where k equals number of digits in k, in n. Okay, that makes sense, right? And this can be computed. So to continue, this is 1 by sk times probability that this is equal to k. Okay, it's an unbiased coin, fair coin. So it really, it's a very simple matter to compute probability of t equals k. So the first k minus 1 tosses should have resulted in head. So 1 by 2 power k minus 1 times the next time it must be a tail. So 1 by 2. So in all, it is 1 by 2 power k. And I suppose this is clear now. So this is equal to, you can compute what it is. It's an elementary thing, but we leave it at that. Okay, that's it. So here the k, of course, depends on n, but the dependence I have written down in here. If you want, you can write it in terms of the logarithm and so on. Okay, k is basically whatever the integer part of the logarithm to the base 10. Forget it. Or maybe plus 1, I don't know. Yeah, the ceiling function of that. Okay, so let's move on. I hope it's clear. Next to another problem.
Hello, sir.
Yes.
Sir, by k digit, it is always meant that the first digit is non-zero, right? I mean,
Yeah.
counting to.
Yes. So you can count that, no? Yes, of course.
Yes, sir. Yes, sir.
Yes, yes.
Yes.
So it's just you write a integer, positive integer. Okay. Therefore, it will not. It is not zero. So you just count the number of digits.
Yes, sir.
Yeah.
Okay.
So it is like you can say what is this k? I can even write it, k is the unique number which satisfies this property, 10 power k, 10 power k plus 1, strictly less than 10 power k plus 1. That's it. Yeah.
Okay, sir, I got it. Thank you.
You're welcome. Another problem which I wanted to do. Yeah. Let me check the book because I have not. So, okay. We toss the coin n times and observe those which show heads, you toss again. And then now count the number of heads. And x is a random variable which counts that. Okay. So, what is the mass function of the number of heads resulting from the second round of tosses? So I explained the experiment. This is also a problem from the book. I don't remember what the number is, doesn't matter. So suppose a coin is such that probability of head, this time it's a bias coin, let us say, possibly. So probability of tail is therefore 1 minus p. Okay. Now what you do is, the coin is tossed n times. N times. Sorry. No, I don't want to say it this way. Suppose there are n coins, okay? There are n coins, okay? Such that this is the case for all of them, okay? Now, we toss them, we toss these coins, toss them, and those that show head again, that show heads, are tossed again. Again, let x be the random variable. The random variable that counts the number of heads in the second toss. Okay, find the mass function. Find fx. Okay, is that problem clear? So you toss them, maybe head n is 10 perhaps. So you have 10 coins, all of them have the probability of head being p. And so when 10 of them are tossed, some 3 or maybe some 4, we don't know, they show heads, and you toss those coins which show heads once again. And then this time, maybe a few smaller number show heads, and x is the random variable that counts the number of heads in the second toss. Okay, find fx. So here, let's say the following. So always, so proof or answer, whatever. So fx of, let us say k, this is equal to, write the definition, probability of x equals k. So this is the second toss, no? So if the second toss results in k, Well, I mean, if you knew that the first toss resulted in L heads, then you know how to compute it. So we do that. And of course, you have to sum over probability that x is equal to k, given that h is equal to L, times probability that h is equal to L. So this is a basic thing that we are using. And L better be at least k. Okay? We need only care about that. Okay. Yeah, this is equal to, otherwise it's not a mistake. This term will be 0. Anyway, so L bigger than or equal to k. And now this is easy to compute. Yeah. So you are tossing L coins, out of which k show heads. That is L choose k, p power k, 1 minus p power L minus k, times. This is the first toss, no? In the first toss, L of them have turned heads. So this again, just this is up to n. Okay. So this is n choose L, p power L, q power 1 minus p power. Let's just write this: 1 minus p power n minus L. Yeah. Well, you can leave it at that, or you can simplify further. Okay. So this L choose k, so n choose L, L choose k, that simplifies a little. So I write that. So n factorial by k factorial times, I am just doing things a little fast. L minus k factorial. And then here I will have an L factorial and an n minus L factorial. Okay. And p power k, just keep it as it is, p power k and p power L. And this one becomes p power 1 minus p power n minus k. Yeah. Okay. So this L factorial cancels with this L factorial. L is bigger than or equal to k. Now this simplifies a little. How? So let me just think for a minute. L factorial cancels. Okay. L factorial and L factorial cancels. And then I have, I did that, okay. N factorial divided by k factorial, L minus k factorial, and then n minus L factorial. Okay, this p power k, that's a constant, no? This because k is not a variable, k is fixed. So p power k. I'm going to stop this fairly soon after I do the following thing. You see, it is, I don't like summing over L bigger than or equal to k. I would like to sum over L minus k bigger than or equal to 0. Okay. And I have already n minus L factorial here. L minus k factorial is very much present. And this is n minus L factorial.
And replace all the L by L plus k.
No, just 1 second, please. Let me explain. So You see, instead of p power L, I will keep p power L minus k and pull out another. So I put the equality sign here, pull out another p power k. All right. And q power. So this q, this is of course q, but I write it as, okay, doesn't matter, 1 minus p power um, L minus k. Something I wanted actually, N minus k.
Change all the L to N plus K, that will do.
N
And
to
then take L equal to 0 to whatever.
yeah, this I want to write as N minus k. I suppose this is N minus k. This is N. Why did I get this N minus k here? Okay, let me write here N minus k, no problem. That is N minus k, no? N minus k. N minus L factor. Okay, so okay, yeah. So this I want to read, just numerator and denominator multiply by N minus k factorial. So this is p power 2k. Something nice happens when you do that. So t is equal to, I'll put t equals N minus k. T bigger than or equal to 0. Of course, it's limited by value n. So n factorial, let us keep it as it is, k factorial. And then let me write here n minus k factorial. And then denominator also I write n minus k factorial. All right. And then what I have here is n minus L factorial. Sorry, did I do this right? N minus k. Yeah, this is okay. N minus k factorial. N minus L factorial. N minus L I write as L minus k minus L minus k. I think that is better. Factorial. Okay. So, and L minus k factorial. So L, this is equal to L minus k. I'm going to change it to t in a minute, but in the numerator, what do I have? I have p power L minus k. No? And here I write that q power n minus k, but I write that as 1 minus q, 1 minus p power n minus L. Should I write that way? N minus. Then there'll be one more term missing, k minus L, no? P power. I wrote something here. I got lost track of what I wanted.
So 1 minus p to the power n minus k it is.
N minus k, but so here it is n minus k, choose something. Yeah. So you see this term and these two terms together forms binomial quotient, no? N minus k factorial, n minus, so it will be n minus k, choose L minus k. So, and then I want to write this as exactly this. I think if I write like this, it will be okay. It's just another way of writing the same thing, but I'm writing it like this. So this is equal to p power 2k and summation. This time I'm going to put t 0 less than or equal to t less than or equal to n, whatever. And then this n choose k. That is actually a constant with respect to the term. This doesn't change. And this one, n minus k, choose t. and then write it as p power t and q power, yeah, so 1 minus p power whatever, q minus t, no? N minus L. No, this is something wrong I wrote. No. Okay, sorry. This is actually, just keep it as such. N minus k itself. We'll just keep it as such. And this may be pulled out. So sorry about that. I pull it out. And then I get something nice. I don't need to bother, but sometimes it's nice to look at it this way, n minus k. Then this is equal to, but this is, so this n choose k is also, I can pull it out of the summation. N choose k is pulled out of the summation. N choose k, and then summation t. T is bigger than or equal to 0. Of course, it's limited by the upper limit. So this is what I have. And this is equal to, so 1 minus p power whatever I have, I write it p power n minus k. And here p power 2k, n choose k. And this one, you see, this is just 1 plus p power n minus k. And that and this club together to give n choose k, p power 2k, 1 minus p square power n minus k. Or you can think of it as p square power k, 1 minus p square power n minus k. Okay, so this is the simplification that you get. Anyway, this is just some indulgence in binomial coefficients and so on. Okay. Yeah. So, okay, maybe just I should write one conclusion after doing all this work. So this is same as before I put the line here. And this is for you to think about. Is equal to probability of getting k heads, yeah, in n tosses where probability of heads is equal to p square. Why is it so? So why? Is it surprising or no? Think about that. It's an interesting thing to think about. Now let me draw the line here. Move on to the next thing. Um, yeah. Okay. Now I want to talk about independence. I somehow get the feeling that I have discussed this before, but in any case, let us do this once again. So recall, or if I have not done it, it's not a recall. So suppose that so x and y are discrete random variable at the moment, or discrete random variables. We say that x and y are independent if yeah, the events x is equal to x, y equals y are independent if you like, I just put it like this. You know what this means, right? Or independent for all xy. Okay. All right. So, or equivalently, so that is probability of x equals x, y equals y is probability of x equals x times probability of y equals y. And when you have more than two variables, it's exactly as before. So suppose that you can even have infinitely many, no problem. Suppose that since we are discussing discrete random variable, maybe it is enough to just consider only finitely many. Okay, doesn't matter. Or let me just write here xi x alpha and j are discrete random variables. We say that this family is x alpha and j are independent former, or is a family of independent random variables if any finite collection of them, if or any finite number, finite subcollection x1, x2, blah blah blah. Let me write here x I1, xik. We have. So this is an independent family. Probability of xi1 is equal to xi1, blah blah blah, xik equals xik is the same thing as a product. xi r equals little xir. So 1 less than or equal to r, less than or equal to k, and for any for any xi1, I could have written x1. I don't know why I wrote xi1. Probably it's confusing to write xi1 because I'm just down to now. Yeah. So x1 here, xr here, xr, xk here, yeah, x1, xk real numbers. Yeah. Anyway, so it's a most natural thing. We have already described the independence of collection of sets. Here, when you prescribe values for the random variables, you get collection of sets. Yeah, and those collections must be independent for any choice of your finite subcollection and for any choice of these real numbers. So that's the definition. So yeah, I'm okay in terms of time. Let me. So here is one interesting thing that is pointed out, worked out in the book. It's a bit of a surprise, one should say. So this is, you can think of it as an example or a theorem. So actually an example. So suppose that a coin is tossed a random number n times. Okay. So, of course, it's understood that probability of heads is equal to P, maybe a bias coin, so probability of this is equal to Q, 1 minus P. Okay, fine. What about the distribution of N, given that we are given that N is a Poisson variate, Poisson random variable, with parameter lambda. Okay, and then show, so let X be the random variable random variables which count the number of heads and tails respectively. Okay, so you see, just a minute, let me, yeah. So you understand, so you are not told exactly how many times the coin is tossed, okay? But that's a random number, and that random number follows Poisson distribution, okay? Now, let X be the random variable which counts the number of heads, and Y is the random variable which counts the number of tails, okay? Show that X and Y are independent. This is a bit of a surprise, because you see, if you fix the number of times you are flipping the coin, once you know the value of X, Y is the remaining number of times you have tossed the coin, right? So X plus Y is always constant. But that constant is not a constant really, it's a random variable, and which follows a certain pattern, and then this happens. Okay, let us go over the proof of this. So what do you need to show? So proof, so we need to show that probability of capital X equals X, capital Y equals Y is equal to probability of capital X is equal to X times probability of capital Y equals Y for all X, Y in real numbers, but basically you need only show this for X, comma Y in integers, positive integers. Okay. So let us just count this. What is probability of? So you need to compute all these things. There's nothing much to do. Y equals Y. This is equal to, okay. Now, you see, so before proceeding, yeah, this is equal to, see, if the number of heads is X and number of Y is Y, then the capital N has to be X plus Y, right? Yeah. But we sort of do this in the next step, because otherwise it could be a bit of a confusion. So I write here summation over N. Directly it is difficult to compute this. So directly you apply the formula. P of X equals X, Y equals Y, given that N equals N, times probability of N equals N. Of course, this is 0 except when N equals X plus Y. So you write that the next step, this is equal to, summation goes away, sorry. In any case, I think it is always good to write the formula down. Okay, irrespective of what X and Y are, this always happens. Now you think for a minute, N has to be equal to X plus Y. So this is probability of x equals x, y equals y, and n is equal to x plus y times probability of, well, n equals x plus y. So, okay. Now this is, so this is what? This is x plus y. So you are flipping the coin x plus y times, and you want x heads and y tails. So probability of that happening is x plus y choose x times p power x times q power y. And what is the probability that n equals x plus y? N, capital N follows Poisson variate is with n is the Poisson variate with parameter lambda. So probability of n equals x plus y is e power, I suppose e power lambda minus lambda, I always get confused, minus lambda times lambda power x plus y by x plus y factorial. Okay, I could have written n here in the place of x plus y and then written n here. It's all the same anyway. But anyway, see, x plus y factorial cancels. I get, what do I get? I get 1 by x factorial, y factorial, p power x, q power y, e power minus lambda, and then lambda power x plus y. Okay, I just do this simplification next step. Maybe it is better to write it as 1 by x factorial. This lambda power x I club with this one, lambda p power x, and then lambda q power y, and then e power minus lambda. In fact, I am tempted to write minus lambda as lambda p and lambda q, but let's not do that this step. We put a full stop here. Oh, sorry, I left out of y factorial. Maybe I do that along with this. Keep it like this at the moment. And now let us compute what is probability of capital X equals X. Okay, probability of capital X equals X is equal to, write down the formula you get out of Bayes theorem or whatever. I mean, it's a very simple matter. Capital X is equal to X given that n equals, it's not Bayes theorem, it's even much simpler than that. The fact that for varying values of n exhausts all the possible events. That's what is the thing here. So n, p of n equals n. And this time I have to add from 1 to infinity. And now it's actually a binomial thing here. N choose x, p power x, q power n minus x. And then what is this? So this I have done, this, and this computation is exactly as before, e power minus lambda times lambda power n by n factorial. And now again you will have some simplification. This is equal to, what is this? So n factorial and n factorial will go away. P power x by x factorial times n minus x factorial. There's a summation. I should not forget that summation. See, x is a constant, so remember that, okay? And q power n minus x is also a constant. I don't need to worry. And here this n factorial goes away, I get lambda power n, which I write as lambda power n minus x, because I have n minus x factorial here, and I put, sorry, I need to use this. Okay, so lambda power x comes out, no? Lambda power n minus x. So lambda power x comes out, and e power minus lambda also comes out. So in the next step, so here, this n is, although I wrote n equals this, unless n is bigger than or equal to x, I'm going to get 0. This term is going to be 0. So n is bigger than or equal to x. So now I can shift the thing. So here the variable is n. So you see, I cannot pull out this. Okay, let's just write what we get. E power minus lambda. Lambda power x is okay. And by x factorial is okay. P power x is okay. And now shift the thing. So n minus x bigger than or equal to 0. Now put t. Okay. Then I have this t factorial q times lambda whole power t. Correct? Yeah. T power x had been pulled out. And t goes from 0 to infinity. But this is exactly equal. But this is exponential series, right? So I can simplify this e power minus lambda times lambda power x by x factorial. Lambda p power x by x factorial. And this whole thing is e power, what is it? Q lambda. Okay. And that is, see, e power lambda times 1 minus q. So I will rewrite that in that particular fashion. So this is lambda p power x whole power x factorial, and then e power minus lambda times 1 minus x, that is e power minus lambda p. Okay. So similarly for the other thing, y equals y, probability of y equals y is similar, and you substitute that in here, and now you can split it. After this, okay, you are almost done. So similarly, probability of y equals y is equal to lambda q power y by y factorial e power lambda minus lambda q. Okay. And therefore, I can write, so substituting, we see that, therefore, probability of x equals x, y equals y is indeed probability of x equals x times probability of y equals y. Okay.
Sir, so here the number of tosses follow a Poisson distribution, right?
That's right.
Yeah. So like, what does it mean in like real life?
So, yeah, I mean, if you want in real life, okay, so you see, for example, number of telephone calls that a typical office receives in a day is known to follow Poisson distribution. Okay. Okay. Or number of accidents taking place in a city is known to follow Poisson distribution. All right. Now, suppose, okay, I will not say some story which exactly captures this, but you know, So, so this coin toss, I can think in terms of keeping track of. So if there are, see, yes, yeah. For example, you number of sales call that you make, or you number of positive responses that you get in a typical day in a sales office. Okay, so, assuming that it follows a Poisson distribution. Each call, you don't know whether it is going to result in a in a, in a, in a sale deal being clinched or not clinched. Suppose it is clinched with probability P and it is not clinched, so with probability Q. Okay, all right. So number of deals that a typical day results in, or failure that results in over a period of time, that is that n is the number of phone calls, or maybe number of customers coming to a shop. Maybe they just make but they go to a shop and then look at the commodity there, decide or not. I mean, they may decide to buy it, they may not. They may decide not to buy according to probability P and so on. So this is a situation where this type of thing can really take place. Okay, is that clear? So there are situations where, you see, if when you just look at one variable, all right, that is only part of the story. But your experiment and so on may involve several processes, and in order to analyze it, you may have to have a random variable which depends on another random variable. Okay, and this is a situation where you have this type of thing. So this type of thing you really do encounter in real life, like I told you. Okay, so for example, number of accidents, all right. So when there is an accident taking place, you can claim insurance, but the insurance involves a process. So whether a person gets insurance compensation or not may have a certain probability P. Okay, so well, he may succeed with probability P, fail with probability Q. Then you have this number of accidents taking place in a city is not really exactly a fixed number. Day by day, it keeps changing. But you know that the number, the sort of the mass function for it, or it follows a certain pattern, and that pattern is seen to have form a Poisson distribution. Okay, there may
Okay,
be,
sir. Yeah,
that type
it's
of
clear,
thing.
sir. Yeah.
Yeah. So typically in a complex environment, you will have some random variable depending on another random variable, and this type of thing can go on. Maybe there is a multiple of some 3, 4, 5 type of thing. Okay, and in fact, even an infinitely many of them. If I have time, I will talk about Markov processes, and at that time we will see that. Okay, so maybe I stop here for today. If you have any questions, you can ask me. I stop sharing.
So sorry. Oh, okay. I was gonna ask you to like scroll down to the last page. It's okay, sir. I'll look at the notes.
No, if you want me to share, I can share. No problem. It's just one click away. Please go on. So I ask. So what is your question?
I just want to see the last page. I missed a bit when you wrote. So like more, could you go down a bit?
Further down. I didn't do anything after that. I just wrote the answer.
Oh, okay, okay.
You see here, okay, I already wrote it in a certain way. e power minus lambda is sticking out, but this is e power minus lambda p times e power minus lambda q. And then you club it along with this one, and then you get it. You see, you have e power minus lambda p and e power minus lambda q. When you take product, it becomes e power minus lambda p plus q. P plus q is 1, therefore you get e power minus lambda. And these two, you just substitute it, you see that it's okay.
Yes.
Is that okay?
Yes, sir. Thank you.
Yeah. Now I am in a sort of a crossroads. I want to, of course, next lecture I will work out some problems and so on. I can either branch off to Markov processes, or I can continue along the way the book has proceeded. Let me see. I will think. I need to do some thinking about it. Yeah. All right. Let me stop.
Regarding the midsem, what will be the pattern and what will be the time?
Okay, so I'm thinking typically I give 6 questions. Okay, so if it's a quiz, only 3 questions. If it's a midterm, 6 questions, typically 2 hours. Okay, and this is the pattern usually I have. And answer all questions. There'll be no choice. Answer all questions. Yeah, or let me see. In any case, you have to answer all questions. I may do some fudging later on. That is not a matter that we have to discuss now, or even before the exam. I need to announce anything.
Sure, sir.
Typically 2 hours. I may give a little more extra time, and this time doesn't include time for uploading. And I always get complaints that, oh, power went off, I couldn't do this, I couldn't do that. And then after 2 hours you upload the answer. I'm going to be strict this time. If any such thing happens, please inform the TAs by sending WhatsApp message. I'm sure your mobile will be charged completely. You have to have it charged. Even if there is power disruption, you can at least send a message saying, look, I lost power and I'm unable to upload, whatever happens. Okay, so suddenly network connection may go, but your mobile data will be still available, hopefully. Okay, so
Yeah, sure, sir.
you will be given sufficient time to upload your answers. But if you experience difficulties, don't wait for 1 hour to send that message. I usually trust people, and I hope that you will keep that trust. So you see, you are all going to be doing things independently. You are expected to not consult with each other, not look up your notes, not consult any book or something. Whatever problem, I always make the test easily approachable. You may find you may have to work hard to get 100%, but 60 to up to 60%, it should be just a cakewalk, or I mean, it should be easy. If you want to get higher marks, you have to work hard. Okay, but don't need to worry about passing and so on if you have been following the course. If you have been systematically ignoring my lectures, you will struggle. That I can understand. But nevertheless, whatever be the thing, don't worry about the outcome. Do an honest job. I trust you people, and you keep that trust. Okay, that's all. Bye for now.
Thank you, sir.
See you on
Sure,
Monday.
sir. Thank you, sir.
Just to confirm, so this will be a closed book test.
Yes,
Okay, sir.
closed
Yeah.
book, closed notebook, no consultation. Is individually you'll have to do it. Yeah. You see, if I can give you a so-called take-home test or open book, if it is open book, the questions are going to become difficult. I don't want to do that. I want to keep closed book. Exam paper will be accordingly, not complicated. If you have to think for half an hour, that question doesn't deserve to be in an exam. Nevertheless, I will give 6 questions. It should be enough time. I will definitely give you at least 2 hours. Maybe I'll, yeah. So I don't want to say anything more. Okay.
Understood, sir. Thank you.
Yeah. Well.
Is there any sort of writing restriction? I mean, can we just write
What
it?
restriction?
A writing restriction. Can we scan and upload?
Yeah, you can scan and upload. You can convert it into PDF, or you just take a photo of it. And I don't know how exactly you will upload it in Moodle. You people have
No,
experience.
I think
using
he meant like if texting is essential, LaTeX, writing in
No,
LaTeX is
I am not
essential.
expecting you to do LaTeXing. Just write by hand, take photo of it, that is scan it, then upload it. Yeah, if possible, convert it in PDF and upload it. If you don't have time to convert it in PDF, upload it as a, JPG file. You must have done it already for assignment, right?
Yes.
Yeah.
Yeah.
Okay. Yeah, if you experience difficulty, please inform, keep me in the loop, I don't have WhatsApp, but you can at least send me SMS or something, or send an email. You have to somehow convey to me if you are facing difficulty. I hope there will be no difficulty. Practice it at least. Find out for yourself how long it takes to upload. You tell me if you want to. I think 20 minutes should be sufficient time. I want only brief answers. I don't want you to write dozen pages or 20 pages. Okay. It should be over in 6 pages. Okay. Yeah. Okay then. Bye.